Hello everyone, and welcome to AISC's live webinar, Fastener Fundamentals, presented today by Chad Larson. My name is Brent Liu. I am with AISC's Continuing Education Group, and I will be moderating today's presentation. I want to introduce today's speaker, Mr. Chad Larson, who's the Vice President at Lejeune Bolt Company in Burnsville, Minnesota. Chad has worked in the fastener, manufacturing, and distribution for 25 years. His background includes production, quality, sales, and executive management. He's also been very active in the committee work, as you can see from this list here. He has served as the RCSE/ASTM liaison and the RCSE secretary and treasurer. He currently is the vice president of Lejeune Bolt Company, and he also serves as the chair of the ASTM Structural Bolt Task Group. He is the vice chair of ASTM F16, the Fastener Committee, and is also the chair of ASTM 1602, which is the subcommittee on bolts, nuts, and washers. We're very pleased to have Chad here with us today. Chad, thanks for being here. I'll hand things over to you.
Okay, thank you very much, Brent. And I'd like to thank all of you for attending, and thank AISC very much for putting this together. It's truly a pleasure to be presenting for all of you today. I will be covering a number of topics today. Here's sort of a list of what we're going to be talking about. And not going to be covering a lot of topics. Bolting is a pretty complicated issue, and most of the things that we're going to be touching on are in and among themselves hour-long to day-long seminars to truly understand, but I'm hoping to skip just enough across the surface of these that you can have a chance of coming away from this identifying areas that maybe you think you should know a little more about based on your own circumstances, as well as some useful in-depth information on a few important topics as we go along, the items that we tend to see the most issues with as a supplier. What we won't cover, what we simply don't have time to get into, are some things that you can definitely find information on in other places. And as we get to some points of that throughout the presentation today, I'll give you some ideas where you can get that. But certainly there's a wealth of information out there in the form of formal educational programs, all kinds of information on the internet, and all kinds of people that are willing to do additional training to give you more information on any one of these topics. What I do want to make clear is I'm going to talk about a lot of problems, a lot of potential problems, a lot of things that engineers can put in place to try to avoid having situations arise at a job site. What I don't want you to leave this call with is this feeling of panic from having seen these problems. By and large, we have very few bolting quality issues in the industry relative to the number of fasteners that are used. As an engineer, if you spend multiple years on one project or maybe do a few projects a year, your exposure to that is very, very limited. But as a supplier that supplies thousands of projects and deals with hundreds of fabricators in a year, we're exposed to a lot of it, and we see a lot of things that you may not encounter in your career, much less on a weekly basis. And so keep that in mind as we go through. There's no need to run from this presentation thinking that some structure you designed is going to fall down. It's simply to give you a better understanding about bolts. One thing I would recommend, Geoff Kulak, I think 3 years ago, gave a presentation on bolted connections and forces and how they act on bolted connections. Now that is still available on the AISC website, and I would encourage you after this, if you didn't participate in that, to possibly go out and grab a copy of that. That's some good information that is left out of my presentation simply because it's available there, and I didn't see the need to spend some of our time going over that. Why should you know some of the things that we're going to be going over today, and what does it matter to you as an engineer? It's my opinion that understanding bolts is really going to help you make more informed engineering decisions up front. Understanding bolts will help make your intentions and requirements clear downstream, clear to the fabricator, clear to the erector, clear to the ironworker. Making informed decisions up front can really help you decrease the likelihood of any problems that might come up down the road. And key for me in all of this is preventing problems prevents compromise. And what I mean by that is buildings go up. They go up with problems and they go up without problems. And we see situations, not just with fasteners, but throughout construction in general, where things come up and people have to make a determination on whether something is fit for use. It's not often that an owner wants to wait an additional 12 weeks for a casino to open because some special bolt that got ordered was found non-conforming and needs to be reordered and remade. There typically needs to be points of compromise where you need to know at least enough about the subject matter to not feel like you are risking the integrity of a structure by seeing something as being fit for purpose or fit for use. And understanding a little more about every element in your craft is very important to that end objective. And fasteners in particular are one of those sort of little thought of last use items that oftentimes are in situations like that, where maybe the coating thickness is a little bit thin. Maybe some problem has happened at the job site. And it comes back to the engineer record to make a determination on whether that really matters or not for the structure or how much. There is a big difference between panic and understanding in terms of dollars, but sometimes a very slight difference in understanding that could lead to that. Examples of that I'll talk about a little bit as we get further into the presentation. So I think it's also important to recognize that however good your intentions may be, your intentions don't always make it to the project. Oftentimes bolts get out to a job site with very little oversight, little QC if any oversight. And you need to find ways to make sure that your intents are carried all the way through to the end use of the product. A little bit about structural bolts and how they work in connections. A bolted connection really takes an army of people, AISC, RCSC, and ASTM. Essentially, components of each of those need to be put together to have a properly designed connection. AISC, since you all have found your way to this talk and to the website to get information on it, assuming everybody on the phone here is familiar with that, but obviously the American Institute of Steel Construction is sort of the steward for steel construction and responsible for promoting steel construction in our industry. What maybe not all of you are aware of is the Research Council on Structural Connections. That is a nonprofit volunteer organization essentially charged with doing research, converting that research to practical application. So it's one thing to have data and information, it's another to make it work in the real world. That committee maintains and publishes the specification for structural joints using high-strength bolts. And that document can be found either in your AISC manual, on the AISC website, or on the Bolt Council website. Those links are there available for you. ASTM, most of you may be familiar with the term. It's actually called ASTM International. Is really the world leader in the development and delivery of consensus standards. And what that means, at least for the purposes of this phone call, is that there's a ASTM committee, the F-16 committee, which is 225 of the 30,000 ASTM members. Those 225 people are essentially all volunteers that maintain the structural bolt nut and washer standards. It's important to remember, a lot of people don't understand that ASTM, being a volunteer committee, there is no technical staff. They essentially rely on committee members to answer any questions that might come into ASTM. Recognizing that these are volunteer organizations, recognizing that a lot of needed changes don't happen right away, it's important to recognize, I think, that these organizations are never really aligned in real time. In fact, sometimes they are as much as 5 or 6 years apart. If a new coating, for example, gets into an ASTM standard, if it just missed a publishing date for the RCSC spec, it may be 5 years before those are aligned. And it's important to recognize that sometimes the industry moves at a pace that's quicker than our standards can keep up with it. So a little bit about how nuts and bolts are made. Not going to get into a terrible amount of detail here, but I think it's interesting for people basically to see the process. Going from a wire rod or a coil to an upsetting stage, to a heading stage, to an extrusion to create a pintail, if in this case it's needed on a twist-off type bolt, thread rolling, and heat treatment. This is typically done in a cold forming operation, or what we call a cold forming operation, which is really used to make literally thousands of configurations of parts. And the cold forming process itself, it may have a few tweaks from manufacturer to manufacturer, but generally follows this flow from steel coils to an annealing process, to a pickling or a cleaning and coating. The wire is then drawn down to size, cold formed by heading and typically roll threading. It's then quenched and tempered as a heat treat process, plated or coated as required, inspected, and then packaged. And again, I think it's important to recognize that to really understand cold forming, you probably need to spend a couple of weeks in a class to really grasp it. Inspection in particular, there are a lot of elements in inspection and quality assurance that need to be well understood. Thankfully, most of your contractors and suppliers are taking care of all of those issues. I put a link here for Discovery Channel actually did a little 5-minute How's It Made video that I thought some of you would find interesting, and we didn't think it was a good time to try to stream that to all of these people, but after the presentation, if you want to throw that link into your web browser, there's a good quick 5-minute video that basically shows the cold forming and the hot forming process. And this is just a little bit of information on cold forming, what it's good for, and a little bit of information on hot forging, which is very similar to the steps that I just showed you that are outlined for cold forming, but it's done at an elevated temperature at a point where the steel is very pliable and relatively easy to form. There are advantages and disadvantages to each of these, and without getting into a lot of detail, I've provided some of these for your review. In particular, the hot forging is really good for long lengths that don't necessarily fit in machines, or for large sizes that would require a lot of forging pressure if cold. In most cases, though, hot forging is a pretty manual piece at a time process. There are a few exceptions to that. Cold forming is a very sort of high volume automated process. The thing to recognize about hot forging is sometimes those bolts are made from blanks to speed delivery, and what I mean by that is a manufacturer may make a 1.5-inch diameter by 2-foot long blank, and as orders come in, they can cut inches off of that and then thread the part to meet certain delivery requirements without necessarily having to set up to make every specific length. Threads are formed in two ways, typically thread cutting and thread rolling. Thread cutting is sort of self-explanatory. That's typically done with a chaser or almost a lathe type of a setup. Thread rolling is actually done with two dies that have the profile of the threads included. And basically what they do is, under very high pressure, roll the threads into the bolt, so there's no cutting. There are some advantages to thread rolling. There's a little bit better strength because of the sort of the cold working, and the grain flow is maintained rather than cut away. Nuts are made. Here's a picture of a progression that shows nut forming. It's very similar. Typically in structural bolt sizes, all of the diameters of nuts would be what we call hot formed. Again, at very high temperature, where there's a cut-off blank, an upset, sort of a partially formed hex shape, a pierced blank, and then a tapped final product with heat treatment, depending on the manufacturer, going on at different stages throughout that process. And again, the progression for hot forming is very similar to cold forming. Includes a couple of different steps, possible descaling depending on the end use of the product, but same process for quench and temper, tapping rather than rolling, and plating, lubrication. We do have specifications that require lubrication in a number of cases for structural bolts, so that's one of the key components to the nut manufacturing. As far as bolts go in general, beside how they're made, there are sort of some universal thoughts on things that you should understand about bolting. Here are some basic terms that I think most of you are familiar with, including clamp force. Elastic interaction, you probably intuitively understand what that is, but it's the way that multiple bolts in a joint might interact together. As you tighten one, the ones around it loosen. A good example of that is putting the wheel nuts on your car, for example. You go around and tighten them once, and you come back to the first bolt and it's light. That's sort of an interaction between all of the fasteners in that assembly. For us, that mostly happens during the snugging process. Embedment, grip length is the thickness of all components in a joint between the bolt head and the nut, or the thickness of the grip. We're typically using that to determine our bolt length. I'll get into this a little bit later on, a nut factor, or what we call a K factor. which is sort of a constant that gives us a relationship between torque to tension. And I think you're all familiar with preload. There's a couple of things I'd like you to take away from the talk today. In particular is just understanding the curve. And what this is I think you've all seen at one time stress strain diagrams on different materials, including fasteners. Understanding the curve is really essential to understanding how fasteners work, and understanding threads is essentially how fasteners function, how they maintain their strength is also really important. So those are a couple of things that I'm really going to try to drive home today, just so you have an understanding. Bolts typically function very much like this stress-strain diagram here, where we've got stress and strain. And what we call this linear range here, or the elastic range, is the tension that we can reach in a bolt up to the yield point, or up to the point where it deforms plastically permanently. This elastic range is any point along this line we can tension a bolt, release the tension, and it will go back to its original length. So we could bring a bolt all the way up to its proof load, or its what we would call a typical clamp load, for example, relieve the tension, and it would go all the way back down to its original length. Some structural bolts are installed in that sort of elastic range, but a very large majority of them, in particular bolts that are installed using the turn of the nut method, are actually pulled well up into the what we would call the plastic range, meaning that there's some permanent elongation. It would be very typical using the turn of the nut method, for example, to bring a bolt all the way up to the peak or the ultimate tensile, possibly even farther. That tends to work fine. It works okay for structural bolts. It works good for one application. You wouldn't want, again, I'll use the wheel bolts on your car as an example. You wouldn't want them slightly stretched every time you had your tires rotated. So for the most part, every sort of advanced fastening industry tensions to a level that's well below yield point. Structural bolts, you need to understand, are a little bit different. They are very typically brought into the plastic range, just as a function of how they're installed. Now, we don't normally look at stress and strain. We do it sort of indirectly, but we do it in different ways. We tend to look at tension and angle, or degrees of rotation and tension, or torque and angle, or torque and tension. We have a lot of different ways that we tend to look at fastener performance as a curve, not always directly related to that stress-strain diagram, but essentially showing the same information. And this is just sort of an example that I pulled to show what would be typical of what we would call a torque tension angle curve, where with the equipment we can actually plot the tension curve, we can plot the torque curve with degrees on the bottom and tension along the side, and torque in foot-pounds on the other axis. A lot of the testing that we do to try to determine fastener tension and bolting behavior is using a signature curve, very much like this. And that's an important thing to understand. If we had the ability to see that in a connection as bolts were being installed, it would tell us exactly what we were doing to every single fastener. Signatures are very unique. You could put 6 of them in front of me, and they're sort of like, I've seen so many of them, they're sort of like children to me. I can tell just about everything I need to know about an assembly by looking at them. I can tell whether the bolts are long or short, whether they're plain or galvanized, whether they're A325 or A490. I can tell whether they're lubed or unlubed. I can tell whether the washer spun during the installation or if the bolt rolled in the hole. There's a lot of information that we can gather by doing a torque tension angle curve such as this. And the technology that we have today allows a lot of people to be able to look at that information, not quite in real time in the connection, but certainly in fastener testing. Some bolting basics, things that you should just understand about bolts. Nuts should always be stronger than bolts. That is sort of a universal truth. The reason we want that is we prefer that bolts fracture rather than strip. Stripping is a condition that could happen in a connection and you wouldn't necessarily know that you had compromised the connection. Tensile failure is sort of immediate and in your face, and it at least tells you that something has gone wrong. Generally speaking, the more bolt threads there are in the grip, the better. Bolts are essentially very stiff springs. Most of the stretch that occurs in a bolt when it's under high tension is in the area of the highest stress, or the smallest diameter, which is in the threads. As a bolt is tensioned, most of that stretch is happening in the threads. If you haven't left very many threads within the grip, you're sort of relying on that small number of threads to do an awful lot of elastic stretch, and sometimes they don't have the capacity. Generally, we like to see more threads available within the grip in a well-designed bolted connection, but structural connections are unique in that they have a lot of design considerations for keeping threads out of shear planes and therefore keeping threads short. Thing to take away from this, though, is if you are trying to detail a bolt length and you are left with trying to decide whether it's better to have 2 or 3 threads sticking out or only 2 or 3 threads in the grip, honestly move the nut out towards the end of the bolt if you can and leave more threads in the grip. It'll just generally provide for better bolting performance. Lubrication is essential to performance in virtually every type of fastener assembly. Torque has a bad name in our industry because of how we use it, but torque can actually be a pretty good indicator of tension. The Navy uses it to hold torpedoes in submarines. It's used to tighten virtually every fastener in your automobile. Torque is used in a good number of applications and can be very good if it's controlled, but one of the problems is it's a difficult thing to control in our industry. Rolled threaded bolts are typically stronger than cut threaded bolts. Fine threaded bolts are stronger and more vibration resistant than coarse threaded bolts. Large diameter parts are more difficult to heat treat properly. When we get up around 1.5 inch, 2 inch diameter, it's sort of like cooking a really thick steak. It's hard to properly heat treat a part because it cannot quench at the same rate, and so the core of the part tends to be much softer in hardness. The outside of the part tends to be much higher in hardness, and that makes it difficult for the part to sort of uniformly distribute load. And we tend to get a little bit nervous as parts get larger. They become much more difficult to heat treat, and heat treat is essentially what gives us all of the properties of a fastener. For large diameter fasteners, you also have to consider that they're typically hot formed, and those can come with die fins and some tooling marks. Long bolts can be difficult to keep straight through the heat treating process. If you're trying to get through 18 inches of steel with a 1/16 of an inch oversized hole, sometimes that can be tough with really long bolts. Another sort of universal truth for fasteners is most of the stress in an assembly is on the first few nut threads nearest the grip. That is just how the load is distributed. And it's important to understand that many quality problems are a result of heat treatment and thread fit, and that's why we will typically spend so much time in the fastener world talking about that. As I mentioned, torque can be valuable, but it's complicated. It's a great means of fitting up and snugging structures. It can be accurate when it's controlled. It can provide for very uniform loading, in particular, again, in the snugging process. It is, however, a little bit wild and variable in the way that our industry uses it. Sometimes we have bolts, nuts, and washers from different sources showing up at a job site, and we truly don't know what's going to happen to torque in that situation. And torque when installing a bolt from the head can be quite different than torque when installing from the nut side. So it's important to recognize that. Threads are very important. Obviously, without threads, fasteners are pins, right? It's what makes nuts and bolts work. And it's important to have a little bit of an understanding to how screw threads function. There's actually over 120 different elements to screw thread design. It's incredibly complicated. Thankfully, our standards allow us to ignore pretty much all of those, but there are a few things that are important to understand. Inch series structural bolts are always what we would call a unified coarse or a coarse series of thread and a class 2A tolerance. As I mentioned earlier, threads do not load evenly, sort of like very long connections. Threads tend to be loaded from the grip out as the bolt starts to stretch. Again, the threads closest to the grip get a disproportionate amount of the load, and it's important to recognize that and what effect that has on design. Rolled threads, again, can be 5 to 15% stronger depending on the grade of the fastener, but cut threads can easily meet specifications. So again, don't be afraid if somebody has supplied your project with bolts that have cut threads. They can more than adequately meet the requirements. Many quality issues that we run into as a supplier are the result of threads or functional thread fit. And what I mean by functional thread fit, it's one thing to have a thread that is perfect coming off of the machine, But after it goes through different coating operations, gets handled, gets dumped out at the job site, thread nicks, coating thickness, things like this tend to have an influence. And we see quite a few problems coming from that. It's also important, as I said, structural bolts have much shorter thread lengths than cap screws. Not going to spend really any time on this slide other than to give you an example of some of the things that go into thread design. It seems relatively straightforward until you actually start looking at it and thinking about the math. Again, thankfully we can ignore most of that and just understand a few basic terms. The root is essentially the bottom of the valley in a thread form. The flank is the side of the thread, either side. The crest is the top. The minor diameter also generally equates to what we would call the stress area on the fastener. The major diameter is often very similar to what we would call the nominal diameter, but not always equal. Thread angle, all of the UNC fasteners that I talked about are 60-degree thread forms. And the pitch. The pitch is something that we're going to spend a little bit of time talking about because there's a lot of confusion on what thread pitch is and what thread pitch diameter is. There's a little bit of confusion. So as this slide comes up, pitch versus pitch diameter. In the bolt and nut world, we use pitch diameter a lot. Pitch is very simple to understand, pitch diameter not so much. And so I'm going to try to explain pitch diameter, but to be quite honest with you, a lot of people in the fastener industry don't understand it. So I'm going to try to explain it in as simple a way as I can. Pitch is simply thread spacing. So if you ordered an inch series 7/8-9 by 2, that -9 means there are 9 threads per inch, and that is the spacing of the threads. There are, as it implies, 9 threads per inch of length. Metric fasteners do it a little bit differently. They would use an M22 by 2.5 by 40. In that case, they don't do threads per centimeter, for example. They do 2.5 millimeter as the spacing in between threads. So the top of one thread form to the top of the next thread form is the spacing. Examples then are unified series fine, unified series coarse. You can have the same fastener with a fine thread of 14 per inch or a coarse thread of 9 per inch. Pitch does not equal fit, however. Implying that pitch equals fit would suggest that you could put any diameter of bolt on any fastener that met the same pitch. And a very simple example of that is you cannot put a 1-inch 8 nut on a 2-inch 8 bolt. It simply doesn't work, even though they have the same number of threads per inch. It's very obvious why it doesn't work. And yet you can get each of those in an 8 thread per inch variant. So we, aside from pitch or spacing, we need what we would consider just a functional size. How do you measure the pitch diameter? And pitch diameter is essentially if you were to draw a cylinder through the plane of the threads, concentric with the threads, intersecting the thread flanks at equidistant points, that would be the pitch diameter. And it's a complicated thing to measure and it's a complicated thing to understand. But essentially it's the diameter across the threads from theoretic thread center lines. And this gets a little bit complicated because we're talking about theoretic thread center lines, not actual thread center lines. Pitch diameter is the functional size of a given thread form. Honestly, a lot of manufacturers don't even measure pitch. They have gauges established at the max and the minimum permitted condition, and they simply use a go-no-go function to make sure that the part that they're making is in between those. But they don't often measure the exact pitch diameter because it is a complicated thing to measure even in a production environment. And back to this drawing that I had, in this particular case, the diameter pitch, again, is the center line. If you took a equal distance between the theoretic top and bottom of that 60-degree angle, this pitch diameter is a line that travels through the center of that. In this case, though, you can see it's neither the center of the external thread nor the center of the internal thread. It's actually just in the center of the theoretical center, I should say, of those. And now to measure that, keeping in mind that threads have a helix angle to them, or a screw form to them, in order to measure that diameter, we're essentially trying to measure the distance of these 2 points on a crest across, or on a mountain, I'll call it, across to the other side 2 points on a valley. The dimension from that point to that point across is what we call a pitch diameter. And why that's so important to fasteners is we use in the structural industry a lot of fasteners that are coated. These coatings, while they cannot change pitch, imagine hot dip galvanizing a bolt. You don't change how many threads per inch they are, but you drastically change how that bolt and nut interact with each other, and that is a function of the pitch diameter. And I've made some very simple sort of graphics here to oversimplify the drawing that I showed with the pitch diameter. If we have a nut thread on this side and a bolt thread on this side, and an approximate thread form of how they are shaped, when these are loaded together, essentially the strength of a fastener assembly is the resistance for this nut thread to shear through the area of the bolt thread, because we know the nut's stronger, so it's going to put up with more force or more stress than the bolt thread will. Essentially, the strength of the bolt thread then is the cumulative area across this bottom portion of the triangle as it wraps around the threads on the bolt. And so that essentially is the stress area of the thread. Now, when we add coatings, they have a significant effect, because if you can picture measuring coating on a plate, for example, if you add coating thickness, it has a one-for-one relationship. The coating thickness is the coating thickness. If you add coating thickness to a cylinder, the effect on your cylinder is double the coating thickness, because you're measuring it on both sides. Since we measure pitch in 4 places, the effect of a coating on a fastener is that it has a 4-to-1 multiplier on the thread fit. And in the case of something like mechanical galvanizing, where we are coating both the bolt thread and the nut thread, it actually has an 8-to-1 multiplier. So what starts out as a relatively thin coating, we have to multiply that thickness times 8 in order to come up with its effect on thread fit, and that can be significant. If you've got a notebook in front of you, many of our coatings are approximately the thickness of a sheet of paper. That in itself doesn't seem like much, but now if you put 8 sheets of paper together, that's the cumulative effect that we encounter in trying to mate coated bolt and nut threads, and it's very important to understand. And why it's important to understand is, here's an example of now we've had to go from the old nut profile, and to accommodate those coatings, we've got to what we call oversize or overtap the nut thread. So forget that blue line, and let's look at it with an overtapped or an oversized thread, which is typical of virtually every coated fastener that we can use. And you can now see where the minor diameter of this nut would intersect under load that triangle of the bolt thread, and we lose a significant amount of strength in oversizing fasteners, and that's why we have an overtap limit established within our bolt specifications. Exceeding that limit gets to a point where thread stripping is not only possible but likely, and it's important to understand that effect when you select coatings, especially with some of the new coatings that are coming out. As an industry, we don't have a lot of history with oversizing higher strength nut threads and the effect that that has on a A490 or what you guys would call a Group B equivalent fastener. We're still sort of learning a little bit about that. This is an example of a gauge that's used to measure what we call a single point measurement, measuring one thread for pitch, and this is an example of a multi-point measurement. This will take into effect accumulations of coatings across several threads. It will also take into effect variations in pitch along with pitch diameter. It's sort of a complicated topic, but it's important. I mentioned that fasteners are a 2A, 2B fit. Not going to worry too much about that today, other than to understand there are different thread classes. There are very tight tolerance threads, which are a 3A, 3B fit, sort of a mid-tolerance fit, which is used on structural bolts, and a loose tolerance, which really isn't used on much of anything anymore. But it's also important to understand that these overlap. So even in using very simple gauging, sometimes if you measured a thread form, you couldn't necessarily tell there's a dimension that would qualify as a class 1A, a 2A, and a 3A. And so all that's important to take away from that is that it's sort of a mid-tolerance, not super well controlled, but somewhat controlled thread form. Thread lengths, while we like to think they are all equal, it's kind of funny that thread length is not a controlled dimension typically on bolts, at least not on structural bolts. We control the body length, a minimum body length for a given length of bolt, and we control the overall length. We control the transition length, which is the area in between the full body and the fully formed threads. Honestly, the threads are whatever is left, and sometimes that number can vary a little bit depending on how manufacturer's tolerance. For you as engineers, it's important to understand the minimum body diameter and what effect that might have as you design connections that are either shearing through or not through thread planes. It's also important to recognize that not all threads are created equal. All of these are 7/8 by 2 bolts. They all meet with each manufacturer's interpretation of the dimensional standard. One has no body at all but is threaded up close to the head. One has very little body and essentially transitions down to threads, and another has a very small body, a short transition, and threads, and technically all of these gauge to meeting the requirements. I find it silly that we actually have some customers that want this particular bolt because they actually believe that if they can get the 1/4-inch plate that they're bolting together to fall somewhere in this transition area, that they can use a few less bolts and consider that a threads excluded design. What happens, of course, if the supplier sends them this bolt? That's why we generally tell people to exercise caution. If you're using really thin plies, understand what that means for thread length. Threads are what make nuts and bolts work. The mating component should be obviously properly mated, not just in terms of size, but also of strength capacity. Unfortunately, we get called in a lot of projects where they've had problems, and we see some pretty interesting things. This particular connection actually has 3 different nut grades: finished hex grade A, a heavy hex grade A, what used to be a grade A nut that stripped off, a DH heavy hex nut. This is an example of a stripping failure where this connection was not able to develop the tensile capacity of the fastener. And to add insult to injury, they were all galvanized nuts on plain bolts, so obviously not properly mated. And here's another example where there's a negative stick out. In that condition, that assembly may not be able to reach its full capacity. And it was actually put on backwards. Some nuts actually have an intentional bearing face with raised markings on the other side, and this nut happened to be put on with the markings down, which can affect the tensions you get with things like turn of the nut method. The bearing face was facing out. Shear. I think pretty much everybody on this presentation is going to understand when we talk about shear. When you're doing your connection design, you honestly, it's one of the first things that you're going to look at when you're designing a shear or bearing connection, is whether or not you've got threads in the shear plane. Sometimes it is very simple. In fact, sometimes you can just put your bolt in a connection the opposite direction and increase the shear capacity, because you can get both shear planes to fall on a body instead of one shear plane falling on the threads. If you have a connection like that, it's super, super important to make sure that that follows through to the, you may be designing this beautiful structure with all shear and bearing connections. You've done that so you can stay away from pre-installation testing at the job site. All of this happens. You send these bolts out and the iron workers put them in the wrong direction, and now one of your shear planes falls into the threaded area rather than on the body. It's important to recognize that, and again, I mentioned early on, make sure that those requirements carry all the way through. When you design your connection, you have to stop for a second and think, now what if somebody puts this in the other way? Where does that shear plane fall? And whether you need to provide direction on where those threads need to absolutely be so they don't get put in backwards. Sometimes they'll get put in backwards just because of assembly or installation clearance. The iron workers feel they have no choice. Without knowing the difference, they'll spin it around and put it the other way. Again, understanding shear, we name bolts things like A325N, A325X. Sometimes that's not understood when it gets to the distributor because it's really a design call-out, not a bolt call-out. The bolt will be exactly the same. The difference is in an X is obviously that the threads are excluded from the shear plane, and an N type is that the threads are included in the shear plane. Lubrication. This is one of the things that is really important to fastener performance. We don't require it in every case for structural fasteners. I could make an argument that it should be on every structural fastener, but other people could make an argument that it's a waste of money and it's not necessary. To understand lubrication, we have to understand a thing that we call K in the fastener industry. And I need to be a little careful. There's a K factor within steel design. There's a K factor within fastener design. Some people call this a nut factor. Some people call it a friction coefficient. The important thing to take away from this is that K is simply a way to define the relationship between torque and tension. And what this means is that if we can define that, we can try to make it repeatable. We can come up with lubricants or coatings that give us a consistent torque to tension relationship. K, however, only works within the elastic range. Once a bolt has gone beyond yield, we can't really use it anymore. So it can only be measured before permanent stretch. There's over 50 variables that have an effect on torque-tension relationship, and this is, one of the reasons torque can get a bad name. Is if it's not controlled, it can be quite variable, and there are a number of things that can affect that. Just to give you an idea, an as-received bolt nut and washer out of the keg from a manufacturer might have a K factor of 0.2. Again, this is just a numeric value, and I'll show you how to get to that value on the next slide. But that can be pretty variable depending on the coolants that are being used in heat treatment, the potentially rust-preventive oils that are sprayed in the keg before the bolts are packaged, any sort of secondary processing that might be done, even things like magnetic particle inspection, where essentially a cleaning solution is used to remove some of the lubricants that are present in manufacturing. Even that can change the K factor. What we typically see with fasteners that are lubricated is a lower value. 0.1 to 0.17 covers a pretty broad range of everything from wax and Teflon lubes up. A really high K factor would be if we took, for example, a hot tip galvanized bolt nut and washer, put them together with no lubricant. The 0.28 K factor would indicate a really high level of friction. We can come up with this value by basically going through a formula. If we know what the torque and the tension is, we can use this formula to get a K factor. And essentially this formula up here will give us that for any diameter of bolt. As an example, if we have a 3/4 by 2 inch bolt that has reached 35,000 pounds at 300 foot-pounds, that is a pretty efficient or effective lubricant. That would give us a K factor of 0.137. We can also, if we know a K factor, we can reverse that equation and come up with a torque out of that as well. The reason I bring this up is we get questions pretty much every week, and I'm sure AISC gets a lot of these, is what torque should I install a 3/4 by 4 inch bolt to? And we sort of laugh because in the real world we have lubricants and coatings that are down as low as a 0.09 K factor. And we have dry bolts out of the keg that have had most of the oil sort of drip off, and we typically on any given fastener assembly could see anything from a 0.09 to a 0.25 K factor on any given day. And what does that mean for torque now? If we apply that math to reach minimum tension on a 3/4 inch bolt with a let's say it's a dacromate coated assembly with a supplemental lubricant, which tends to be very slippery, I actually by hand could reach minimum tension with a spud wrench on a 3/4 inch bolt with a very low K factor or an effective lubricant. But it also could take as much as 470 foot-pounds to reach the same tension with a dry bolt nut and washer. So it's really impossible. This is why we worry so much about torque in this industry and how variable it might be, is really any of those are possible with any given fastener assembly depending on the condition that it's in. Other industries that are a little farther along than ours, Japan for example, they actually sell all of their structural assemblies as matched sets in different categories. One of those happens to be that the assembly has to be between a 0.15 and a 0.17 K factor. In that case, you can use torque in a pretty reliable manner because there's really not that broad of a range when that K factor is controlled. It's when we don't control it that's a problem. Another way of looking at this is decreasing friction or increasing the effectiveness of a lubricant decreases the effect of torsional stress on a fastener. And torsional stress can cause fasteners to fail at a much lower level than they would without that torsional stress. And a good way to look at that is, here's an example of a 1-inch A325 bolt. This is the AISC minimum design tension for that size and grade. This is the minimum tensile strength. Nobody makes their bolts right at minimum, so if we took a typical example of a bolt that is quite a bit above required minimum tensile, this line that goes along here would be representative of a very low K factor of a 0.10. You can see that for very little torque input, we can gain a high level of tension. What's important to see in this is that the, bear with me while I grab my pointer again here, this curve that sort of follows along here is the strength that can be reached at any one of those given K factors. What I mean by that is an effective lubricant like that 0.10, we can develop almost all of the tensile strength of the fastener because there's no twisting motion being applied to the threads at the same time that they're being pulled. In a more typical range, like the 1.5 to 1.7, we actually lose quite a bit of the bolt's capacity to torsional twisting or those torsional forces that are being applied at the same time. At a really high K factor of a 0.25, it may actually be impossible to reach minimum fastener tension before we twist the bolt off in torsion. And that's why that 0.25 is established by the Federal Highway as a maximum K factor for their bridge and highway work. So why wouldn't we just lubricate everything? That's a good question. Why wouldn't we just lubricate absolutely every structural nut that had to be used? One of the problems with lubrication is the better the lubrication gets, the better it is for the performance of the fastener. Unfortunately, a lot of our structures get painted, and the better these lubricants are, the harder they are to remove and the more resistant they are to paint. And so there's some very practical sort of considerations if you just sort of wholesale enforce the need for lubrication on your fasteners to get better performance. You need to recognize that someone's going to pay for that later on, possibly the painting contractor coming back asking for additional money because he didn't realize how hard it would be to paint that structure. Thankfully, almost every industry has a solution. There are a number of people that are supplying now lubrication. The 563 nut specification now recognizes this type of lubrication where it is on one bearing face and the internal threads only. This allows you to specify a lubrication for the performance of the fastener, but it makes the fastener also very easily paintable. Essentially the same galvanized finish on the nut as you would have on the bolt. And this has taken off in recent years. It's been around for probably 10 years, but not that many people are aware of it. So. Now down to bolt selection, the structural bolts themselves, they're sort of broken up into strength groups. I consider them 120 and 150 KSI families. The AISC refers to them as Group A and Group B. This is sort of how they shake out if you look at them in terms of just minimum tensile. But we have other ways of looking at it. If you're building a bridge, for example, that's using a Type 3 steel, we can also separate these by raw material type 1 and type 3. And you can see that most of those grade A and grade B variations are available in either of those types of steel, but it sort of complicates whether you're looking at strength or raw material as a first step. You can also look at them by style. You know, if you are going to install heavy hex heads or twist-off type bolts, there are varieties of each of those. Typically, this is a decision that sometimes comes from the bottom up. It comes from the erector or the fabricator saying, hey, we'd like to use this particular style. Sort of like the lubrication trade-off, you know, as strength goes up, we tend to lose ductility. Ductility is a good thing for structural fasteners. So you sort of have to balance things out. Sometimes the design requirements are the design requirements and you need the highest strength that you can get. But quite honestly, the lower strength level fasteners, they're widely available. If you have a problem, they're pretty easy to replace. They're very ductile. We like ductility in our structures. We like a lot of bending and twisting and moving before things fall down. There are more coatings available. There is generally less risk, and when I say that, that means a lot of different things, from hydrogen embrittlement to quench cracks. But if you absolutely need the strength, that higher strength level Group B fastener is really the only way to do it. It's important to keep in mind that also these are specified minimums. Most 120 KSI or Group A fasteners nearly meet A490 or Group B tensions or clamp loads if used appropriately. And they certainly come close to meeting their tensile requirements as well. So there tends to be a little higher safety ceiling in terms of exceeding minimum requirements with the 120 Group fasteners. Other standards to be familiar with: the heavy hex nuts, A563 grade C and C3 can be used on the Group A plane only. The C3s are for weathering. The 563DH is the most common structural nut. Those can be used on A's and B's, the DH3 for the weathering equivalent. And of course the washers F436 Type 1 and Type 3 are used on both the Group A and B for plane coated and weathering applications as listed. We sometimes reference some other standards. 449 and 354 are referenced within our structural bolt specification. Some examples of that are if for whatever design reason you need a countersunk head. If you have thick plies that need to be pulled together and you don't think the standard thread length might be enough. If you need larger than 1.5 inch diameter. If you need a coating that is not specifically permitted by A325 or A490. These are good opportunities to use 449 and 54. One thing you should be aware of, though, is that 490 will send you to 354. And then when you get into A354, there's a couple little notes in there that you have to read to really understand. And basically what it says is if you go to 354, is that while the reference to go there would make you believe that it's a direct equivalent, it really is not. When you order a 354 in place of an A490, a good supplier will ask you if you want heavy hex instead of standard hex, because a 354 would not be a heavy hex by default. You should consider specifying a max tensile, because there's no max tensile strength in 354 like there is in 490. You should consider specifying carbon decarb testing, which is not a requirement of 354, but it is of A490. You should consider specifying magnetic particle testing, which is a requirement of A490 but not A354. And again, be very careful with the thread length. You will, by default, get longer threads on an A354 than you will on an A490 unless you specify the thread length. So keep that in consideration as you design connections that might be using 354s that are shear or bearing type. And on to coatings. Again, moving along quickly. There are a number of coating options, a number of new coating options that have become available, and some that are on their way. B695 is pretty common as a mechanically deposited, or MG zinc. That is for Group A fasteners only. Hot dip zinc. This specification changed a few years ago. It used to be A153. And on the F16 committee, we wrote this F2329, which is sort of a fastener-specific hot dip zinc coating. You still will find probably some DOT and engineering references to the old hot dip standard, but this is the new one. F1136 you may know as a dacromate or a geomet coating. F2833 is a new coating that was approved last year for A490s. Can also be used on A325s, essentially any of the Group A or Bs except twist-off bolts. And the metal building industry, for example, uses a lot of just electro-deposited zinc fasteners for their buildings. There's a virtually unlimited number of other possible coatings for the Group A fasteners. There is at least one other coming through the balloting process for Group B fasteners. It's important to keep in mind with these coatings that they are not always done by the manufacturer. Distributors around the country are not sitting on every possible diameter and length in every configuration of coating. A lot of times they're sitting on plain fasteners and they send them out and get them coated when a certain project comes along. Assuming that they know all of these things we've talked about, thread fit and the effects of K-factor and supplementary lubrication, is sometimes a pretty big step. So it's important for you to understand what you should be looking for in order to pass that on. Again, keeping in mind that these coatings can have a significant effect on thread fit and on the K-factor. Another thing to understand about coatings, thickness is only measured on significant surfaces. In the case of a bolt, that would be the head, typically on the flats or the top of the head. We don't really try to measure coating thickness within the threads. Coatings are not typically corrosion tested on a lot-by-lot basis. A lot of engineers over the years have said, well, let me see the salt spray test results on this. Typically that is done at the process level or proven out by the platers, and it's very rarely done on a lot-by-lot basis. And so typically not a huge problem, but one of the reasons this doesn't happen is some of these salt spray tests can take 14 days or longer. There's oftentimes 14 days of delivery available by the time an order is placed and when it needs to be in a connection. And so for the most part, those tests are done on sort of a production level basis, not on a lot-by-lot basis. Hot tip galvanizing is on external threads only. The internal threads of a nut are actually tapped after coating, and you basically have bare exposed metal on the internal threads of a nut when parts are hot tip galvanized. That's simply because the coating is too thick and pools too much in the threads, and the oversize required to accommodate that thickness would not allow the threads to develop any strength. Really important to recognize is that the industry has yet to establish any oversized tolerances or limits for these new coatings on A490s. So everybody's sort of flying along with their own recommendation at this point. We're working on that in ASTM to sort of standardize that, but that work has not been done yet. So again, understanding thread fit and coatings. Nut threads need to be oversized for most coatings. Increasing the pitch diameter also increases the minor diameter, which decreases strength. Oversized nuts have less proof load capacity. We know that. In fact, the DH nut has a lower proof load test requirement when it is oversized than it does when it is not oversized. If you are using coated nuts on A490s and the nuts are oversized, the nut may be proof load tested to a value below the minimum tensile strength of the bolt, and it's important to recognize that. Sometimes excessive oversizing can change the failure mode from bolt tensile strength to thread stripping. Keep in mind that bolt tensile and nut proof load tests are performed on fixtures, and those results don't necessarily correlate to assemblies. And an example of that is a nut may pass a very high level of proof load on a hardened fixture that's not stretching or elongating or has no torsion on it. The fact that it didn't strip at a certain value in a test doesn't mean that it can reach that same level when it's put on a bolt whose threads may not be as perfect when the bolt starts to stretch and is undergoing the effects of torsion, and the bolt threads are actually shrinking as the bolt is getting longer and stretching. So you can't always correlate test results to real-world performance. Extra care should be taken not to over-tension coated fasteners. And this is really a hard thing to define because our industry has always said if you didn't break it, it's not too tight. But we're starting to see some things with coated fasteners that I'll explain in a second that I think you should understand. You should also understand the specific coating. The different coatings, we have different grades and different classes. In this particular example, F1136 or Dacromit. Grade 3 should be used on the bolt and the nut, but you need to make sure that you're on the bolt and the washer. Grade 5 should be used on the nut. The grade 5 includes a supplementary lubrication, and it's really important for those fasteners to be able to perform as intended. For some information on that, there's a link I put down on the bottom of this slide here. You can go out to the Bolt Council website and get some information on Dacromit and Geomet coatings. Some of the things maybe to look out for or to consider while we wait for our specifications to get a little bit caught up. One thing to really remember is that coatings are not elastic. We know that bolts are elastic and they stretch back after they've had a certain amount of load. I don't think people realize how many galvanized and coated fasteners end up in connections looking like this. And I find it comical when an inspector comes along and rejects a lot number of nut because it has 0.1 mils too low coating thickness, and then you take a few bolts out of the connection and you show them what really matters looks like, which is the threads which have been stretched so much during the installation process that they have no coating anyhow. This is an important consideration, and you really should think about putting some controls in place to make sure that bolts are not excessively tensioned when they're coated. And that's a hard thing to quantify, and that's something that the industry is going to have to work on here a little bit moving forward. Job site requirements. I'm not going to go into a lot of details. Some of these are in Geoff Kulak's presentation I mentioned earlier, but you can also just see the RCSC spec for details. To be quite honest with you though, you can make most problems at job sites go away if you simply are having proper storage and handling procedures followed. And assuming the bolts are requiring some sort of tension, that there's some level of pre-installation tension or QC oversight that's being done. In this case, this project, they actually erected a building to store the bolts in because they recognize the importance of storage and handling. In this example, on the right-hand side, while not terribly organized, at least these bolts are up inside the actual deck section of a bridge, protected from the environment and protected from moisture. Examples of not good storage and handling. These I sort of laugh at. We've been to a lot of job sites where we see this type of thing. Bolts that have been covered with plastic, unfortunately, after most of the kegs are already full of water. We also see bolts that come back and get just sort of resorted at the end of the day from different parts of a project, and lot numbers mixed up, nuts intermingled, etc. This is the type of stuff that leads to problems, and if you can put some controls in place to make sure that doesn't happen, you will be doing yourself a great service. Pre-installation testing, when bolts are required to be tensioned, we all understand, I think, that some pre-installation testing needs to be done. That can be as complicated as this particular project actually had some pretty high-end testing equipment, put a trailer on site specifically to do fastener testing. But it can also be as simple as just having a tension measuring device or a skidmore available. These really need to be present on job sites where tension is a requirement. Now, just because tension is not a requirement doesn't mean you could ignore QC. We see people falling into that quite regularly, and that's also a problem. I've been called into projects where simple shipping error sent A325 bolts out to a project that was supposed to be A490s. Iron workers opened the kegs, had no reason to notice or pay attention. There were 1x4s. They had to put 1x4s in the building. And some months later, discovered that a simple shipping error had connections in a structure full of A325s when they should have been A490s. The fact that tension is not a requirement does not eliminate the requirement for having some sort of QC or oversight at a project. Installation methods. Again, I'm going to ask you to, rather than spending a lot of time on it here today, go see the RCSC specification pertaining to installation methods. There are 4 that are currently recognized. It's the turn of the nut, the twist-off bolt, direct tension indicators, and calibrated wrench. I'll let the people that try to sell you each of those try to convince you why you should use one or over the other, but the fact of the matter is they all can work very well when used correctly. There are some that have better reputations than others, some that are a little easier to misuse than others. But if you follow the requirements in RCSC, they can all work just as well. By comparison, some other industries use slightly different techniques. Japan, where they have a lot of control over K-factors and tend to trust in torque a lot more than we do. They actually use a lot of torque plus torque, a certain level of torque for its snugging operation and then another level of torque for final tension. In Europe, they use torque plus angle. They use twist-off bolts, DTIs. They use some angle and some torque only methods. But worldwide, this changes a little bit. What's important to all of those methods, you'll see wording to this effect in RCSC, is that there's a snug tight as it pertains to a snug tight or a bearing or a shear type connection, but there's also a snug tight as it pertains to achieving tension in a slip critical or a fully tensioned connection. RCSC has always really struggled with trying to define snug tight, and it's important to read these definitions, try to get your head wrapped around them, and I think what's important is just understanding that the snug tight condition is the point where the plies are in firm and nearly continuous contact, that the bolts have at least some level of pretension. Really important with the turn of the nut method, for example, that you're not using up some of the turn that you think is developing tension to simply pull plies together that are not in contact. What we tend to see is that snug tight has no control whatsoever. We often see bolts that are snugged with a few impacts of a wrench to beyond minimum tension, and we see bolts that are snugged in one continuous operation and then not snugged a second time, and bolts have loosened around bolts that were subsequently tensioned. Snug tight is a thing that's really sort of horribly controlled and neglected in our industry, but really it is going from this condition of some gap in the plates or the plies to a fully compressed joint, and that needs to be done before any of those approved installation methods can be used properly. Typical bolt that you would see at a lot of projects, a heavy hex assembly. For years and years, this was sort of known as the de facto installation fastener type. They are used a lot in shear or bearing type connections. They are used in a lot of tensioned connections, which include the turn of the nut method, which is essentially tension by elongation. And they are used quite a bit in the calibrated wrench method, tension by calibrated torque. Honestly, when we see the calibrated wrench method used, the calibration method is the iron worker, in many cases, just thinking the bolt is tight. We don't see a lot of companies that are actually doing the calibrated wrench method correctly. There are a handful. I'm familiar with a few erectors out there that do it very well and do it very regularly. But in a typical small project without a lot of oversight, a lot of bolts are just going into connections and ratcheted with an impact wrench until the iron worker thinks it's tight. That's his version of the calibrated wrench, and that practice is what gave that method a bad name for a while. But when it's used correctly, it can actually be used pretty well. Hex bolts are also used quite frequently with DTIs, or direct indicator washers. Those essentially function by measuring tension by compression, or a sort of a calibrated amount of preload required to compress the bumps on a washer. One thing I recommend for all of those methods is getting away from impacting tools. There are a number of companies throughout North America, throughout the world in fact, that sell non-impacting and non-reacting tools. They're quite a bit quieter. They save, particularly in coated fasteners, they go a long way in preserving the integrity of the coating, so it's not all getting impacted or beaten off. There are a number of cases where we have had customers give us a call and say, hey, we're working on this project. We don't even know whose bolts these are, but we're missing the galvanizing on all the corners of the bolts. And they send us samples, and we look at it, and we may send them off to do an adhesion test, find out the adhesion is fine, but it's the severe amount of impacting that causes some of that damage. If you're going to go through the effort to specify the coating, if you're going to have people do oversight to see if the thickness is correct, if you're going to do rotational capacity testing, measure fastener tension, and then have all of that wrecked by having some guy out there just knocking away on it with an impact wrench, it's all sort of for nothing. So be familiar with and use some of the technology that's out there. These tools are lightweight, they're non-reacting. They can be used with virtually any of the systems that I just mentioned, the DTI washers, the turn of the nut method, the calibrated wrench method, and we recommend doing that. Again, the turn of the nut method, a lot of people don't completely understand it. It's pretty simple, right? You snug tight, turn X number of degrees, and you're essentially guaranteed some level of tension. The problem is all of the criteria for snug tight were established essentially starting at low or no tension, and we know that very few connections actually start like that. In fact, in most cases, again, this is an example of that torque tension angle curve that I mentioned earlier. Snug can be pretty variable. It can happen anywhere from 10 degrees of rotation to 300 degrees of rotation. We never really know what is snug when iron workers are just using impact wrenches to sort of bang away and develop tension. But very typically, we see snug tensions that are significant. Even me with a spud wrench can probably turn a nut about 60 degrees and develop a pretty high level of snug tension. In this case, that would be 20 or 25,000 pounds of tension on a 7/8 diameter bolt, for example. That becomes the point where we measure 0 and, in this particular case, add 180 degrees of turn. And this is where I find it interesting that we have the ability now to really see what's happening to capture this data as we install bolts, nuts, and washers and capture the degrees and the tension and the torque. The turn of the nut method, it's great because what it relies on is getting up here into this area of stretch, and you're always using some amount of the stretch. But the tension varies little in that range, even though the degrees change a lot, essentially because it's all just plastic deformation of the fastener. So we see it as a very consistent method simply because it gets up into that plateau and they're all being stretched, and they're all being stretched to some different amount. But what's important to remember in that is without lubrication, for example, it's very possible that you go from a snug condition here to an installation requirement of 180 degrees, which allows a plus 60 degree tolerance, which gets really close to the fracture point of that fastener. Not necessarily wrong. Thousands, if not hundreds of thousands of bolts are installed in that manner every year, and we don't have buildings falling down. But if you were a fastener engineer, trying to develop an application for a fastener, you wouldn't strain it to that level, and you definitely wouldn't do it when the fastener was coated. So there are some downsides to the turn of the nut method, even though it's very tried and true. It's a great low-cost method of installing, but there's a better way out there, and that has to do with controlling that snug. DTI washers, again, these are the washers that I mentioned that function on compression. They're available in a couple of varieties. Standard washers that measure gap, another variety that's called a squirter type washer, which has a silicone that emits from the sides when they're tensioned. Those, as I mentioned, are typically used on heavy hex bolts. Occasionally they're put on tension control bolts. They can be placed under the head or under the nut. And again, one of the 4 approved methods that can work well if used correctly. Twist-off bolts, I think most of you are probably familiar with that. These are essentially bolts that provide for a single-side installation. They provide a visual indication that at some point there's been enough of a torque reaction or hopefully enough tension developed based on that torque-tension relationship that the spline shears off. These essentially work on what we called before, which is calibrated torque. In this case, the bolts, nuts, and washers are sold as matched assemblies and have a very controlled K-factor or range of friction that they operate in. And if used correctly and stored and handled correctly, they can be a very good way to tension structural bolts as well. And here's just a quick example of a bolt in its snug condition. You put the wrench on, pull the trigger, outer socket rotates counter to the inner socket. All of that torque is taken up in the spline. When that level of torque is reached, the spline just automatically shears off. And again, these are available in the non-impacting, non-reacting type of tools, both in pneumatic and electric variants. So, rotational capacity test is an important thing to understand. I had hoped to have enough time to cover this in detail today, but I think what I'm going to do is just provide you with this information that's in here. There are any number of sources, including myself, that can give you some additional follow-up information on rotational capacity testing. It's in a bit of a state of flux right now. There's some proposals out there to try to change this test, but if you read through this information on your own time and make sense of some of these graphics, I think it will help a little bit in understanding that test and understanding the value of it to the industry. So getting ready to close up here, some unusual aspects of structural bolting. Bolts are tensioned well into yield very regularly. This is sort of a no-no in every other engineered fastener application. It works well for our industry. It works okay, but there are some limitations to that. In very many cases, our bolts are not sold as matched sets, and that is, again, sort of nearly a requirement for every other type of fastening industry. We intentionally have thread lengths that are very short, yet we know that bolts perform better with longer threads. So we're sort of designing all of the best criteria in a well-performing fastener out of it to meet our requirements. It's a little bit counter to what might be good engineering practice for steel is not good engineering practice, unfortunately, for fasteners. A lot of our acceptance testing is done in the field, which is often the first point of assembly, and that's a little bit backwards, and our industry will need to address that a little bit moving forward. We have no industry requirement for K-factor for assemblies, unlike many other established structural industries that have matched sets that are sold in essentially K-factor ranges. Snug tight, as it pertains to fully tensioned bolts, is a very highly variable element for our industry. Again, I don't want you running to the hills worrying about problems, but what can happen? I've had direct personal experience with everything on this page. So while we say that things don't happen often, if you're in this industry long enough and you're called in on enough projects to either consult or supply or take over or whatever, you will run into a lot of these. Not to cause anybody to lose any sleep, but these things happen. We see some of them frequently, some of them very rarely, but it's everything from fatigue to quench cracks to head bursts to torsional and tension failures to lack of installer training. These are things that can happen at job sites, and there are things that I've just mentioned that you can try to do to help some of these things or prevent some of these things from happening. But ultimately some of it just comes down to the quality of the parts that are being sold. And what you might see, what we see quite often are surface discontinuities. There are relatively minor discontinuities that we would call a burst or a seam. Burst is sometimes a seam that opens up. A burst is sometimes just a result of the forming operation. Trying to move steel when it's cold occasionally causes the steel to sort of burst or split open on the periphery. Some people see that and sort of freak out, think it's an absolute big problem. In most cases that is not. It's sort of just a forging surface defect. We have permissible limits for these established within ASTM on sort of what's a permissible and non-permissible amount of burst. But it can make people uncomfortable when they see it, even though it may not affect the performance at all. There is a difference between a burst and a seam, although sometimes seams sort of split open and turn into bursts. We see them occasionally on nuts. We see them more frequently on bolts. We do tend to see them more on round-headed or twist-off type bolts than we would on hex-headed bolts, simply because a good portion of a hex-head bolt is actually trimmed off as one of the last operations, so a lot of those bursts may have existed and then been trimmed off in a operation. In this particular case, all you can do is measure them and see if they can form, but honestly I've never seen a burst that was actually so bad that it affected the mechanical properties of a fastener. But I have seen a lot of people get really excited and shut down a lot of projects as a result of seeing them. Now, you don't want to discount some sort of a seam. In this case, there are seams from the raw material processing on a nut. And in this case, what you might think is a seam on a structural bolt, which is in fact a quench crack. Seams are not that bad. Quench cracks can be horrible. Quench cracks are not super common, but they do happen. I have a feeling a lot of them end up in structures and are not caught. We actually have started to see more of them in recent years as A490s are starting to get coated. This particular example is an A490 that was coated. I don't know that this crack would have been identified visually by anybody on a black fastener, but since it was coated, it happened to get caught by our QC people here on receipt inspection, and ended up having to basically segregate and scrap that entire lot. They happen. They happen as a result of a severe quench, often of a high hardness alloy material. And again, there are no doubt thousands, if not hundreds of thousands of bolts with quench cracks in them in structures around the country, but typically not in high enough quantities to affect a particular project or another. We don't see them very often on nuts, but they can happen occasionally on nuts, and occasionally they don't run longitudinally. We see them as a result of laps or thread laps and thread rolling, for example. In this case, this black area is the depth of a quench crack through the root of a thread. Again, other problems that we run into, trying to pull thick plies together without full engagement, reported as a thread stripping problem, everything from counterfeit bolt to defective material. In fact, ultimately ends up just being not enough engagement to support the load. One time had a problem brought to our attention, wondering if the zinc was properly adhering. We actually found out that the zinc had really good adhesion, but in trying to fully tension this bolt from the head side, the connection had slipped so much into bearing that they could not even turn the bolt to generate any tension. It was simply bound up in the steelwork, and through all kinds of ratcheting and hammering away with an impact tool, they basically drove all the coating off of the corners of the threads. Again, could have been avoided if they had understood the benefits of hole size in that particular case. making sure that there's not a bound bolt so they're able to generate tension. And in this case, maybe using a non-impacting tool could have saved some of that coating. We had a customer last year come to us and say that some washers they were using were too brittle and they were cracking on installation, and they sent us samples and we couldn't figure it out. I'd honestly never had a washer crack in my experience. Through some additional investigation, we found out that they were putting inch series washers on metric fasteners simply because they fit. They got them mixed up at the job site, and the radius underneath the bolt head was actually putting so much outward pressure on the washer that they split. And once they realized they had mixed up some components, that got fixed quite quickly. And other things you might see, tool marks on hot form bolts, for example, perfectly acceptable, perfectly compliant with the standards. Burnishing marks or fixture marks. Sometimes we get thread stripping as a result of reamed nuts in the tapping operation. We're seeing more and more people that for whatever reason are installing bolts from the head side, and sometimes they are completely twisting off the bolt heads, again because of the bearing or the friction in the hole on the body of the bolt. And once in a while we see something like this, which is just that's just hard to explain, you know. That got through so many levels of engineering and QC and ended up like that. So. And again, we see overtension a lot, in particular with some coated fasteners now that have very slick lubrication properties. We see bolts coming out of connections that have trained installers. They've been match marked, they've been witnessed, they've been signed off, they didn't break. We consider them a good installation. But in reality, you know, we've already lost to partial stripping these first couple of threads. Actually, a better way to look at it is this would be the depth of engagement for the nut if it were still installed. Essentially stripped the first thread and a half, haven't done much damage to the threads farthest from the grip. But we're seeing a lot of galvanized fasteners with really effective lubricants being installed to that condition. And now that we're using coatings on A490, we've seen some very limited cases of stress corrosion cracking as a result of that high level of tension creating micro-fine stress cracks in the thread roots, which are then susceptible to sort of a delay fracture or stress corrosion cracking. And that's one of the downsides that we're starting to see from some of the coated high-strength fasteners. And rust. We take a lot of phone calls on rust. How much rust is okay? The truth is we can't answer that question. The RCSC spec says that if you've got any fastener of any type that's in a condition that's been altered from when it was tested, that you need to requalify it. In this particular case, who knows? These twist-off bolts may be retested and absolutely turn out to be fine. They may not meet tension, but the test needs to be done to requalify. Something that's this far gone, as the example on the right, is probably just scrap. I won't cover these, but some good reading if you want to look some of this up to get more information on bolts. Absolutely do that and gain some more knowledge. And aside from that, what else can you do? Get additional training. If there's a few things you picked up on in this presentation that you're interested in, find a way to get more information. A number of options are out there. Get more familiar with the standards. Ask questions of those above you in rank and above you in age, and those behind you who are maybe have just learned something new. Ask questions. Get involved in committee work. There's no reason not to be involved in RCSC or ASTM and become more familiar with some of the standards. Work with reputable contractors and suppliers. That goes a long way. And I think last but not least, be willing to work through problems. Again, projects move forward, and engineers that really know their stuff understand when they can compromise and when they can't. So that's it. I know I covered a lot of ground in a short amount of time, and I think in part that was to show how much there is to know about nuts and bolts, but in particular I hope you picked up on the torque tension angle curves, what that means to fasteners, what threads mean, what that means for coatings, and again sort of a brief overview of the installation methods. And with that I'll end it and turn it over for any questions that we might have.
All right, thank you very much, Chad. We do have a little bit of time for a few questions. I want to ask a couple of you, Chad. I'm going to slide back to slide 59. This question actually came up from a few different people. The question is this, in regards to transition threads in the shear plane, should these be considered A325X or N?
In RCSC, it was determined that anything that was in the transition area could be considered the full body. Now, we know, depending where it falls in that transition, there can be a considerable difference in the strength. That transition essentially goes from what we would call the full body diameter down to approximately the pitch diameter. The thought at RCSC is that minor reduction, since it doesn't go all the way down to the minor diameter of the thread, that minor reduction in strength was not worth taking into consideration when shear planes fell in the transition. They can be considered full body.
Okay. Next question. Is Dacrymet a proprietary coating, or is it a generic ASTM coating?
Dacrymet is a trade name and a patented process, as is, and this is something important to note. We're seeing a lot of people use Dacrymet lately, but we're seeing quite a few people starting to specify Geomet. Geomet is from the same company. It's a non-chrome containing equivalent to Dacrymet. It's not equivalent in necessarily salt spray performance or corrosion protection, but if you need a coating for an A490 and for maybe some environmental reasons, you have to be careful not to use a coating that contains any chrome. Geomet is another option. Now, the F1136 specification was written around the specific processing parameters of Dacrymet and Geomet, so it's not in the sense that it's sort of an open consensus standard that anybody can copy. But there are a number of other zinc aluminum coatings out there that don't necessarily infringe on any of the trademark or patent information or requirements for Dacrymet and Geomet. And some actually have their own name. So there's another like zinc aluminum type coating that's out, which is a MagniGuard, and a company called Dorkin has another zinc aluminum type coating out. So there are multiple suppliers for what we call that family of coatings. And what's already happened in Europe and what we're talking about doing in the U.S. now is once these 3 or 4 zinc aluminum coatings exist, we will eventually try to wrap them into one standard, with essentially the differences being the branding, the trade names, and the marketing. So.
Okay. We'll move to slide 75. You were discussing the use of A354BD bolts. The question is this: we use quite a few of these type bolts. Do you have any recommendations or suggestions for a good reference on the use of these bolts?
If you're using A354, it is typically to get around something in A490. And what I mean by that is not getting around something in terms of sacrificing safety, but getting around a limitation. Size is often one of them. A490 bolts stop at 1.5 inches, but what if you need a 2-inch diameter bolt? That's when people go to 354. It's simply important to recognize that 354 is not an exact equivalent, and so if you're using 354s, what you might want to do is call out your bolt dimensions to 354, specifying a heavy hex head, for example, with whatever thread length you want. And then you can say with the mechanical properties and other tests performed to A490, meaning you sort of want to invoke the test requirements of A490 on this 354 specification, which will give you your mag particle testing. It'll give you your carb and decarb testing. It'll give you your max tensile. However you can work that out with your supplier so you all understand what you're getting is how I'd recommend that you do it.
Okay. And then I'm going to move back to slide 72. The question is in regards to looking at the two stacks, I guess, of attributes of Group A versus Group B. In Group A, for A325 bolts, you show it as having less risk. Could you further explain that?
Yeah. I touched on this a little bit when I was on the slide. That family, the Group A family, the A325s, A325Ms, 1852s, generally made out of a medium carbon steel, typically quenched in oil, which is a pretty, I would say, a moderate quench. In particular, there is not a lot of risk for quench cracks in that family of product. It doesn't mean that there's a super high propensity of it in the A490s, but I have seen, especially in the last few years, quite a few issues of quench cracks in the Group B product. Thankfully, that's all been stuff that's been caught by somebody, the manufacturer, the supplier, before things got into connections. I don't know if I've ever seen a quench crack in an A325 or a Group A type fastener. When it comes to ductility, Group A fasteners are just so much more able to conform to some of the things that we run into in structural connections. You know, we're allowed up to a 1 in 20 slope before we need to use a bevel washer. And to have fasteners that easily conform to that shape or that bevel or that channel, if necessary, without putting a lot of stress in the minor diameter, the stress area of the fastener. For me, it's sort of an 80-20 rule. 80% of the problems that we see are in this 20% of bolts that are in the large diameter, high strength coated category. And so it's hard to quantify risk. It's more of what you're comfortable with. Can you put buildings together with Group B fasteners? Absolutely. It's done every day, and it's done quite well and quite safely. For us, when we're supplying a project and somebody comes to us and wants a 4140 2-inch diameter, high hardness, high tensile strength bolts with some coating on it, we get a little nervous. And if we get a little nervous, the engineer should honestly be a little bit more nervous. And so it's hard to directly quantify that, other than we have much fewer problems and fewer rejections in a number of categories on the lower strength fasteners.
Okay. Here's a question regarding stainless steel. Is there a recommended stainless steel structural fastener that's equal to an A325 bolt?
Honestly, I'm not familiar enough with that to say. Stainless is sort of an interesting material of itself, and I think I'd defer that question to somebody who had much more background in stainless fasteners than I do. But if the person that asked that question wants to get in touch with me, I have a couple of people that I could reach out to answer that question.
Okay, sounds good. Just a couple more questions here, and then we need to wrap it up. Occasionally, we are requested to provide a torque value for snug tight. Is it appropriate to give them a torque of 25 KSI?
Yes and no. That giving some value is not necessarily a bad thing, but the reality is it may require 50 KSI to draw all of the plies in that particular connection into contact. And that's one of the issues we have in our industry, is that we never really know what we're dealing with on the connection side, how stiff the plies are, how thick the plies are, and how much effort it takes to draw them together. So that is almost as impossible a question to answer as is how much torque does it take to meet tension on the same type of bolt, because all of those same variables exist. It's simply being used to define a slightly different number. We like to see torque being high. In fact, if I were to recommend a torque that people used, it would be pretty high, maybe 70 or 75% of the proof load of the fastener. Simply making sure that you're not stretching the bolt in subsequent tensioning operations, but getting as much tension as you can out of it to assure that you're truly snug. But again, that's going to be different for every different scenario.
Okay. Thank you very much, Chad.